Hi, everyone. How do you graph y equals x cubed, or x to the third? Let's point plot. The cube of 0 is 0. Once again, the graph goes to the origin. The cube of 2 is 8. The point 2, 8 lies on the graph. Sorry, 327 might be too ambitious. All right, the cube of 2 is 8, but the cube of negative 2 is negative 8. So the point negative 2, negative 8 lies on the graph. Remember, for a squaring function or for an even function, if you input opposite values of x, you get the same value. Here, we don't get the same function value, we get opposite function values. Here, the point 28 lies on the graph. I'll do this in green. The point 28 lies on the graph. If that's the case, the point negative 2, negative 8 must lie on the graph for an odd function. The cubing function on R is an odd function. It is symmetric about the origin. What does that mean? The graph is symmetric about the origin. So if I take this graph and I rotate it 180 degrees about the origin, I get the same graph. I could almost do this, right? It's like, I could almost do something like that, right? Okay. Also, if you draw a line, you can draw a line through all three of these points. You can draw a straight line through the origin, any point xy on the graph, and the corresponding point x negative y. Sorry, negative x negative y on the graph. If the point xy lies on this graph, then the point negative x negative y, or opposite of x opposite of y, will also lie in the graph. So, various ways to think about symmetry about the origin. If you rotate this graph about the origin 180 degrees, you get the same graph. The point xy leads to the point opposite of x opposite of y. You always get those partner points. And you can draw a line through the origin and the 2 points like so. All right. Opposite x values yield opposite function values. Okay. Again, 2 and negative 2 lead to opposite function values, 8 and negative 8. Opposite x values lead to opposite function values. F of x and f of opposite of x are always opposites, where x is in the what of the function, the domain. And once again, the domain must be symmetric about 0 to ensure this kind of odd symmetry, so that these partner x values exist. Right. So if xy lies on the graph, so must opposite of x, opposite of y. Right. So officially, when do we have an odd function? A function f is odd. That is, we get that symmetry about the origin for the graph, if and only if this happens. F of opposite x equals the opposite of f of x for all x in the domain of f. So for every x in the domain, that is, every time we get a point on the graph, there's a partner point at the opposing value of x, where the function value is the opposing value. Opposing values of x, the input, yield opposing values for y, the output. Here's a proof. Let f of x be x cubed, where the domain is all reals. For all x in the reals, again, for odd functions and even functions, we want to look at f of opposite of x. And what's the key S word here? Substitution. What happens when we substitute or plug in the opposite of x, or negative x, in for x? Substitution. Substitute the opposite of x for x. So we're cubing not x, but the opposite of x. Now the cube of the opposite of x is the opposite of the cube of x, right? Basically the cube of -1 is -1. That's the idea. The cube of -1 is -1. And then the cube of x is x cubed. All right. But this now is the opposite of the original rule. F applied to x yields x cubed. All right. But f applied to the opposite of x yields the opposite of x cubed, the opposite of f of x. Opposing function values, I'll do this. Opposing function values yield, opposing x values in the domain. Opposing x values in the domain yield opposing function values. If 2 gave us +8, -2 will get us -8 as the function value or y-coordinate. If we replace x with its opposite as the input, we obtain opposite outputs. Now, aside from f of x equals x to the third, what are some other function rules on R that will yield an odd function? Well, consider x to the fifth, x to the seventh, and so forth, even x to the first. We've seen that guy before. How do you graph y equals x? We get this. It's the identity function. The identity function is also an odd function. And in fact, if you have something like x to the -1, x to the -3, these will also give us odd functions, although the implied domain is not R. You have to exclude 0. So why do we call these odd functions? Because any rule, f of x equals x to the n, where n is an odd integer, that will give us an odd function. Here, the domain is all reals for these over here. The domain must be symmetric about 0. All right. Now, how do these graphs compare? It's kind of similar to what we saw before. Okay, here's y equals x for that matter. Here's y equals x. That's odd. Here's y equals x to the third. I think of these guys as snakes. Y equals x is like a dead straight snake. Y equals x cubed is a curvy, rising, tall, proud snake. Y equals x to the fifth. Y equals x to the fifth in green. That's also a tall, proud, rising snake. All right. Notice, away from x equals 0, the green graph is steeper than the blue or the red graph. The green graph is steeper. But if you zoom in close to x equals 0, for values of x like 1/2, for example, or 1/4, or 0.1, or 0.9, notice that the green graph, y equals x to the fifth, is actually very flat compared to the blue and red graphs. So again, if you consider y equals x to a positive odd integer, all right, then we get these snakes. They're steeper and steeper away from x equals 0, but the graphs get flatter and flatter as you get closer to the origin. They all go through the origin. And these all represent odd functions, where domain is R. Are there functions that are both even and odd? Yes. The 0 function on R is both even and odd. Y equals 0. Look at that graph. Is it symmetric about the y-axis? Yes, the graph is even. Is it symmetric about the origin? If you take this thing and you rotate it 180 degrees about the origin, do you get the same graph? Yes, you do. F of x equals 0 on R, the set of all real numbers as a domain, that's both even and odd. Any 0 function where the domain is symmetric about 0 will be both even and odd. Although many functions are neither even nor odd. If I give you something like f of x equals x to the third plus x to the second, what is that? Is that even? Is that odd? No, it's neither. It's neither even nor odd. y equals x to the third. Hey, that's our nice snake. But then try to add x squared. That's messed up. We lose both even and odd symmetries. That's messed up. It's neither even nor odd. That's typically the case when you add an odd and an even function that aren't zero. Next up, more powers of x. By the way, at this point, you should be able to graph anything of the form y equals x to a positive integer. What's the graph of y equals x to the first? It's a line, dead snake, dead straight snake. How about y equals x to the second? That's a bull. In fact, it's a parabola. Y equals x to the third. That's a rising snake. That's curvier. Y equals x to the fourth. That's a bull, but not technically a parabola. How about y equals x to the 99th? That's a snake. Steep on the outside, flat on the inside. X to the 100th. That's a bull. Again, steep on the outside, flat on the inside. Next up, y equals x to the 0.